Okay, so hi everybody. So today we're going to go ahead and go over 4.6, which is change of bases. This is kind of out there, I'll be honest. So hang in there. We'll go slow. We'll get through it together. Okay. So let me just rearrange my notes a little bit. Okay, so definition 4.6.1. If S is the set, which is V1, V2, all the way up to Vn, is a basis for a finite dimensional vector space V, and if we have V under S, which is given as C1, C2, all the way up to Cn. Now, in the last section, we actually talked about what this meant. You have a vector under some sort of a basis S, and this is going to be the coefficients that go along with it. Okay, so is the coordinate vector of V relative to S, then the mapping V onto VS creates a one-to-one connection between the vectors, in the general vector space V and the vectors in the familiar vector space Rn. Okay. And I'm going to label this 1. Okay, this is equation 1. Okay, so we call 1 the coordinate map from V to Rn. Okay, now we're not going to write it like this anymore. We're not going to write it with parentheses because we want to write it, we want to like kind of make this transition over to matrices. So from now on, we're going to write this. We write this as the vector V under some basis S is going to be given a C1, C2, all the way down to Cn. Okay, so that's how we're going to write it. We're going to write it as a matrix. Okay, so recall exactly what we're doing here is you have a vector, okay? Now, the hard part about this is you want to define what that vector is. Just consider it to be like floating around in space. It is where it is, okay? So you have this vector and we need to define it. We need to call it something. Well, we're only going to call it something based off of whatever that potential basis would be. So it's defined based on that basis. So in this case, the basis is S, and under that basis S, we're going to call that vector C1, C2, all the way down to Cn. I could call it something else as long as I define what the other basis would be. Okay, so here's what we're going to get into. The change of basis problem. Okay, how exactly do we do this? Okay, so if V, you got to write small here because there's a lot of stuff to be written down here. So if V is a vector in a finite dimensional vector space, I don't know why I wrote an S there. space v, and if we change the basis, or sorry, the basis for v from b to b prime. Okay, so once again, you have this vector space that's defined under basis b, and we're switching it over to b prime. Okay, how are the coordinates? How are the coordinate vectors? V under the basis b and v under the basis b prime related. Okay, so what we're going to do is we're going to explore this in R2. Okay, so we're just going to look at what this would be in R2. Okay, so we have two bases here. Okay, so one of them is going to be B, which is going to be the basis U1, U2. Okay, and you also have the basis B prime, which is given as U1 prime, U2 prime. Okay, so remember, we're just calling R2 in two different ways. We're defining it in two different ways. One of them is under the basis U1, U2, and another way is under the basis U1 prime, U2 prime. Okay, so what I'm going to do is I'm going to say we're going to let so U1 prime under the basis B. Okay, so it is here first. This is where it starts. And we transfer it over to the basis B. I'm going to call that the basis AB. And the vector U2 prime under the basis B is going to be the vector CD. Okay. Now I know this is starting to get confusing because, like, what are you talking about? You're in basis B, but then you're in basis B prime, whatever it is. Remember that this vector is just an arbitrary vector in space. And if we don't define it, you just consider it to be like this object floating out there. Now, how do we define it? Well, one of the ways that we're going to define it is in B prime, under the basis B prime. But that same vector can then be renamed, relabeled in the basis B or under the basis B. Okay, so just two different ways to call the same exact vector. Okay, and so that's what we're going to call it. So such that I have U1 prime is equal to A U1 plus B U2. Okay, and then I also have U2 prime is equal to C U1 plus D C2. Okay, so remember that since it's a basis, we can write it as a linear combination of the other vectors. Okay, so that's all I've done there is I've just simply rewritten it as a combination, linear combination of the vectors. Now we okay, what about the vector V under the basis B prime? Okay, I'm going to simply label that K1, K2. So what I know then is I know V can be written as a linear combination of these because we're under basis B prime. So I'm dealing with U1 prime and U2 prime. So this is going to be K1 U1 prime plus K2 U2 prime. Okay. But what is U1 prime and U2 prime? Well, we've defined them to be up here. Okay, what we're trying to do right now is we're trying to make the connection between the different bases. Okay, so what I have then is I have the vector V is equal to K1 times U1, but U1 prime, but U1 prime is A U1 plus B U2, and then plus K2 times U2 prime, which is given by C U1 plus DC2. Okay, just plugging these into that equation. Okay, now I'm going to regroup and I'm going to put the U1s and the U2s together. So I have the vector V can be rewritten as, so I'm going to put the U1. So I have K1A plus, where else is U1 at? U1 is right here. So plus K2C U1. Let's put the U2s together. So I have K1B plus K2, there should be a U2 here. Sorry. So K2D and times U2. Okay, so what do I know then? I know I can rewrite this vector. So what this is V is now a linear combination of U1 and U2. So that's just a way of rewriting the vector V under the basis B. Because remember, the basis B is given up here as U1, U2, and so everything can be written as a linear combination of those. So I have V then is equal to, and I'm just going to rewrite this as K1A plus K2C, and then K1B plus K2D, which I can rewrite using matrix multiplication as A, C, B, D times K1, K2. But what is K1, K2? We've seen that before as well. K1, K2 is V under the basis B prime. So this is equal to A, C, B, D times the vector V under the basis B prime. And what is this? This, since it was a linear combination of U1 and U2, this is the vector V written under the basis of B. So what did I do? I came up with a relationship between the vector written under base B and what the vector is written under base B prime. So I know then that vector V under the basis B is equal to A, C, B, D times the vector V under the basis B prime. Okay, and that's the relationship that I want. Now we're going to call the vector ACBD, we're going to call this P, and we're going to label this as what's called the transition matrix. Okay? Okay, so next page. That was a lot. Okay, so solution of the change of base problem. So we dealt with the problem before, now how do we deal with the solution? So if we change the basis for a vector space V from an old basis B, which I'm going to label as U1, U2, all the way up to UN, to a new basis B prime, which is going to be equal to U1 prime, comma, U2 prime, all the way up to, comma, UN prime. Then, for each vector V in V, so this is lowercase, and this is the vector space V, the old coordinate vector V under the basis B is related to the new vector, coordinate vector, which we call the vector V under B prime, by the equation, which is what I gave earlier. So V under the basis B is equal to P times V under the basis B prime. Okay, so that's a relationship. So this is the really cool thing about this section is we're basically just figuring out how do we switch from one basis to another, and it's all based off of what this transition matrix is. That's it. Okay. Now the thing about P though is if we go back to here, what were the column matrices here? Okay, the column matrices were what U1 prime under B was and what U2 prime under B was. Okay, so those are what the columns of that matrix is going to be. So this is where the columns of P are the coordinate vectors of the new basis vectors relative to the old basis. Okay, so what that means is we're going to have U1 prime under the basis B, comma U2 prime under the basis B, all the way up to UN prime under the basis B. So these are going to what's going to become like the column vectors. Okay, so what we're going to do is we're going to call this the transition matrices, or the transition matrix. And I'll write this as P, which is going to take B onto, actually we'll go B prime first, B prime onto B. So I'm starting off at the basis B prime, and I'm mapping that over to what the basis B is. And that is going to be given by the vector of these column vectors, U1 prime under the basis B, comma U2 prime under the basis B, all the way up to UN prime under the basis B, and that whole entire thing is a vector. Okay, furthermore, you can make the same argument the other way. So P, which is the transition matrix from B onto B prime, is going to be the matrix of the column matrices of U1 under the basis B prime, U2 under the basis B prime, all the way up to UN under the basis B prime, and that is also a vector. Okay, so there we have it. Okay, now what does all that mean? Okay, because I know this section is a lot. Okay, it's definitely a lot, so don't get frustrated. Okay, so let's try and clear this up a little bit. Let's do an example here. Okay, so consider the bases B, which is U1, U2, and B prime, which is U1 prime, U2 prime for Rn, where the basis B is given by those two vectors, and the basis B prime is given by those two vectors. Now, I know you can't even see it because it's super blurry there. Okay, but this should be U1 prime, and this should be U2 prime. Okay, sorry about that typo. Okay, so find the transition matrix. Okay, so how exactly are we going to do this? Okay, so what we do for A, we observe that U1 prime is equal to U1 plus U2. And U2 prime is equal to 2U1 plus U2. Okay, so let's step back a moment. Okay, where did I pick these things? It seemed like they were just picked out of a hat. And then why did I pick these things? Okay, so let's try and make use of this. Okay, so what I'm doing is I'm trying to go from B prime to B. Okay, that's what I'm trying to do. So what I do is I start off and I'm trying to write each one of these vectors as a linear combination of what would be U1 and U2. So if you take a look here, and I took U1 and I added to U2, so that plus that gives me 1, 1. Okay, so furthermore, I needed to write this as a linear combination of U1 and U2. So what is it? If I took 2U1, so 2, 0 plus 0, 1 gives me 2, 1. Okay, so that's all we did. So what does this mean? I just rewrote these under the basis B. So what this tells me is U1 prime under the basis B is written as the vector 1, 1. And u2 prime, this should be it's horrible that I'm trying to squeeze this in here. This is a comma here. Under the basis b is given, I'm trying to save space because there's a lot going on here, is written as a vector 2, 1. Okay, so those are the two things that I know. Okay, so based off of what the definition up here was, what I know then is I know that the transition matrix that's going to take b prime onto b is given as, you just take these column matrices. So 1, 1, 2, 1. Okay, and that's what that is. Okay, so that's the first part. Okay, so B, now we want to go the other way. So now I want to take and write U1 and U2. I want to take and write those as linear combinations of U1 prime and U2 prime. So pause me for a moment because you should be able to go through and figure this out. Okay, so U1, I need to come up with some sort of a combination between these two that's going to give me this. Well, if you notice, you take U2 minus U1. 2 minus 1 gives me 1. 1 minus 1 gives you 0. So this is going to be U2 prime minus U1. Okay, or another way I could rewrite this is negative U1 plus U1 prime plus U2 prime. Okay, now what about U2? Okay, so now I need to go and rewrite U2 as a linear combination of those. Okay, well, the first one has to be 0, so that means that these have to be the same. So I have to go ahead and multiply this by 2. So 2 minus 2 is going to give me the 0. And then 2 minus 1 is going to give me the 1. Okay, so all I needed today to do is take U2 prime and minus 2U1 prime. Or this is negative 2U1 prime plus U2 prime. Okay. So therefore, what do we know? Okay, I know that U1 under the basis B prime, because that's what I did. I rewrote U1 as a linear combination of the basis under B prime is going to be equal to, well, negative 1, 1. And then furthermore, I have U2 under the basis B prime is going to be the vector negative 2, 1. Okay, so what I know then is I know the transition matrix from B onto B prime is going to be given as negative 1, 1, negative 2, 1. Hold on. For some reason I have this different in my notes. So I just need to double check. So U2, which is this vector, needs to be 0, 1. So if I took negative 2U1 and added it to U2, so negative 2, 1, or sorry, negative 2 plus 2 is going to give me the 0. And then negative 2 plus 1 is going to give me 1, but it doesn't. It gives me negative 1. Okay, so I did that wrong. So this should be a plus and that should be a minus. Now I think it works. Okay, so 2U1, so 2 minus 2 is going to give me 0. And then I have 2 minus 1 is going to give me the 1. So this should be a positive, and that's a negative, that's a positive, and that's a negative. Okay? Now, you might notice that there's a relationship between B prime to B and B to B prime. Okay? Hopefully, you're kind of like seeing what it is. Maybe not, and that's okay. But it turns out that these happen to be inverses of each other. Okay? That's what it turns out to be. Okay, so on to the next page. Okay, which I do believe is the last page. Okay, anyway, so let B and B prime be the basis in the prior example. Use an appropriate formula to find V of B, so this B should be on the outside there, not on the inside. Given that, you have this. Okay, so B and B prime are the basis of the prior example. So what I know from the definition before is that V under the basis B is going to be equal to that transition matrix that's going to take B prime onto B times the vector V under B prime. Well, this is what I'm looking for. I know what this is. I know what this is, so I just have to multiply it all out. Okay, so this vector is 1, 2, 1, 1. and this is the vector -3, 5, and then I just have to multiply them together. So I have -3 plus 10 is going to give me 7, and then -3 plus 5 is going to give me 2. Okay, now what does that mean? Like, what did we just find? Okay, so remember, v is just an arbitrary vector somewhere. That's all it is. Okay, but I need to define it. I need to call it something. So in order to call it something, I have to have some sort of a structure to back it up. Okay, so that structure in the first case is b prime. So if I'm going to call v, if I'm going to define v, but under the rules, the laws, the basis, b prime, I'm going to call that -3, 5. Now, on the other standpoint, what I just figured out here is if I was to call this same vector, that's the same exact vector, but based off of what b is equal to, then we call it 7, 2. Now, that still might not make sense to you. But think of it this way. Your grandma or your grandpa or something. Like, what do you call your grandpa or grandma? You might call it Nana. You might call it Opa. You might call it Papa, Pa. Like all sorts of different ways. Now, your grandpa or your grandma is exactly the same person. It doesn't matter how you call that person. It's exactly the same person. Now, why you would call it that way is defined on the structure that came prior to it, okay? I think Opa is the word for grandparent or grandpa, I think in Swedish, okay? So under that basis, under that background of being Swedish, well, that's what you'd call that, okay? Under the background of like my side of the family, we call it Pa. Under my wife's side of the family, we call it Papa. So it's under those basis that you're going to call that same exact person different things. Okay, so that's the whole idea there. Okay, now, so what we have here is note that we have this idea. Okay, if you took a transition matrix that's going to map b prime onto b, and then times the transition matrix from b to b prime, well, what is that? That is just the matrix that maps b onto itself. It took me a long time to figure this out, and I don't know why it took me so long, but it did. If you look at what this is doing, it looks like these should both be b primes, right? Because you're starting at b prime and you go to b, and then you start at b and you go to b prime. So you start at b prime and you end up at b prime, but that's not the case. The reason why it's not the case is by what's given up here. Okay, how do you multiply matrices? You take a matrix and you multiply it. You take a vector and you multiply it by its transition matrix, but you have to multiply it on the right-hand side. I can't take -3, 5 and multiply it over here. So in other words, if I took this times this, which is going to turn out to be some other transition matrix, and I take some vector that's in this space, I have to put it here, and I have to multiply it here first. So what is that going to do? I have to take a vector from the basis b, which will transform it over into the basis b prime. And now that you have that, you're going to take and you're going to multiply by this transition matrix. That's going to take something that's in b prime and you're going to transition it over to b. So it seems out of order, but it's not. You're going to start at b and you go b to b prime. You're going to get a matrix, and that matrix is going to be in b prime. And you multiply by this transition matrix, which you go from b prime to b. So that's what we have. Okay, well, what does that imply? Okay, what does that imply about this matrix? You start off with a vector, and you end up with that same exact vector. That is the identity matrix. Okay, and under the same notion, I know if I took the transition matrix that mapped b onto b prime, and I multiplied it by the transition matrix which mapped b prime onto b, then that is going to be the transition matrix from b prime mapped onto b prime, which once again is the identity matrix, okay, which makes this a very powerful, important tool. Okay, which leads us to theorem 4.6.1. So if P is the transition matrix for a basis B prime to a basis B, so you're starting at B prime, you go to B, for finite dimensional vector space, then P, which is the transition matrix, is invertible, And P inverse is the transition matrix from B to B prime. Okay, so just the inverses of each other. Okay, so this is going to be a procedure for computing P, which maps B onto B prime. So I start with B and I go back. I'm going to go to B. Okay, B prime. So 1, we're going to form the matrix, which is given as B prime augmented with B. Okay, so you notice we're taking whatever is going to be the new basis and you're going to augment it with the old matrix. Okay, so 2, using elementary row operations, reduce B prime to the identity matrix. Now, we've done this before. Remember, this was called the inversion algorithm. You have this augmented matrix. You wanted to find the inverse. You just took what was over here and you just reduced it to the identity matrix and then out popped its inverse. Okay, so step 3 is going to be the resulting matrix is going to be in the form of I augmented with the transition matrix from B to B prime. Okay, and then the last one, which is kind of stupid to write down, is extract that transition matrix out of there from B onto B prime. Okay, so we can write this kind of up as a flow chart. So if we have the new basis, so we're going to take the new basis, augmented with the old basis, and we're going to do some row operations on here. And we turn this into I augmented with the transition from old to new. The transition matrix from old to new. Okay, so that's what we have. Okay, we're almost done. Hang in there. Okay, so example 4.6.3, use vectors from example 4.6.1 to show that the transition matrix is given here. Okay, so what are we doing? We're starting with the old and we're going to the new. Okay, so what we do is we're going to take the new basis, we're going to augment it with the old basis, okay, which turns out to be what? What's the new basis? Okay, so we got to go back to, where are we at? Over here. Okay, so the new basis is 1, 1, 2, 1. So these are stacked vertically, remember? So 1, 1, 2, 1. So this is going to be 1, 1, 2, 1. Now augmented with the old basis. Now what's the old basis? The old basis is your standard unit normal vectors, so 1, 0, and 0, 1. So this is 1, 0, 0, 1. And then I just have to simplify this to turn this into the identity matrix. So I'm going to take the top. The top is going to remain the same. So 1, 2, augmented with 1, 0. And the bottom row over here is going to become by taking the top minus the bottom. So 1 minus 1 gives you 0. 2 minus 1 gives you 1. 1 minus 0 gives you 1. 0 minus 1 gives you negative 1. Okay, then I need to get rid of this 2. So I have to multiply the bottom by 2 and then subtract it from the top. Now this time, the bottom is going to stay the same. So 0, 1, 1, negative 1. So I'm coming with the linear combination of those to replace the top. So the bottom I'm multiplying by 2. So 0 minus 1 gives you, 1 minus 0 gives you 1. And then you remember, you're multiplying the bottom row by 2. So 2 minus 2 is going to give you 0. 1 minus 2 gives you negative 1. And 0 minus a negative 1 is going to give you positive 1. I forgot. I multiplied the bottom here by 2. So it should be 0 minus a negative 2, which gives you a positive 2, which is exactly what I was trying to find. Okay, so there we are. Okay. And then the last theorem. So let B prime be the set of vectors u1 through un. It's going to be the basis for some vector space Rn. Let S be equal to E1, E2 all the way out to En be the standard normal base. So remember, E1 is the vector 1, 0 all the way out where there's n of those elements in there. The vectors in the base case are written in the column form as this. Now, what in the world does that mean? Okay, let's do a quick example. So say, for example, I have the matrix that's given by 1, and I'm going vertical so you can understand what I'm trying to do here. So 1, 2, 1, 2, 5, 0, and 3, 3, 8. Okay, I'm going to call this the matrix A, and it does turn out that this is invertible. Okay, so what this is doing is this is the transition matrix from the basis, which is U1, which is 1, 2, 1, and then U2, which is the basis, there should be a 1 there, 2, 5, 0, and then U3, which is the basis, 3, 3, 8. And what it's going to do is it's going to map it to the basis, E1, which is 1, 0, 0, because I'm working in 3 space here. E2, which is the vector 0, 1, 0. And E3, which is the vector 0, 0, 1. Okay, so in other words, I can just take what this basis is and I stack them here in column vectors. And by doing so, that is going to be the transition matrix that's going to transform whatever basis I have over into the standard normal unit vectors. Okay, so that's what you have. Okay, so I hope that wasn't too confusing. I think it was a lot, but I've been really trying to work through this to understand it very well. So hopefully you guys are too, and I'll see you in the next section. Okay, bye everybody.